There are a couple of reasons you need to learn embedded C right now. The very first, better hardware understanding. Unlike Arduino, embedded C does not have any abstraction layers and hence helps you understand the hardware much better. Embedded C takes up very less space in the microcontroller's memory, as the microcontroller does not have to store any unnecessary header file. Comparing embedded C with Arduino's language, embedded C has faster speed of execution, which helps in better and accurate outputs. Last but not least, embedded C is the language used in the electronics and embedded systems industry. So if you are looking to enter the industry or looking to build your products more professionally, learning embedded C is a must. So what are we going to do in this video? In a couple of upcoming videos as a series, we will try to learn embedded C from scratch and learn about the GPIOs and registers in a little bit more detail, look at other fundamental functions of the microcontroller, and overall we'll try to understand the hardware and the controller much better in much more detail. What are we going to do in this video? So in this video, we are going to learn what registers are. We are going to know how to control GPIO pins of the ATmega328P, which is the microcontroller used on the Arduino Uno and the Arduino Nano boards. And also, we'll also look at the classic LED blink example and how to control an LED blink using registers and a GPIO. So what are registers? We'll understand registers from here. So before registers, we need to understand what memory blocks are. So memory block, you can think of memory blocks inside a microcontroller as an imaginary box which can hold either a binary 1 or a binary 0, which is a bit. That memory block can hold only one single bit at a time, either a 1 or a 0. A collection of those memory blocks together form a register. In our case, in the ATmega 328P's case, there are 8 memory blocks that come together to form one register, as the controller is an 8-bit microcontroller. Now, inside the microcontroller, there are many registers, and every register is given a particular name. So the next question would arise, why does the microcontroller need registers? So registers are basically used inside of a microcontroller for configuration and interfacing purposes. So we'll understand the same with the help of an example. So on screen you can see a DDR-X and a port X registers. So we'll look at DDR-X register first. DDR stands for data direction register, and X is a substitute value for either A, B, C or D. The A, B, C or D over here stands for the port names. So the main function of the data direction register inside the microcontroller is to hold the status of a particular pin on the microcontroller chip. So for example, if the register was DDR-A, the 8 bits of the register would represent the status of the 8 pins corresponding in that port. So from pin 0 of port A to pin 7 of port A. Now, what do I mean by status of the pin? It is which the pin will act as either an input pin or an output pin. For example, if we want to give an output signal, the pin would be set to a binary high, or the memory block of that corresponding pin inside the DDR register would be set to binary high or a 1. And if we wanted to set a certain pin in a certain port as an output, we would set that corresponding bit inside of a register as a binary 0. So in the Atmega chip, 328 chip, if there is a binary 1 inside of a certain memory block of a register inside the DDR register of a port, you should understand that represents that the pin is acting as an output pin, and if there is a 0, the pin will act as an input pin. Another function of registers, it can be used to be treated as a temporary form of memory, a temporary storage. So for example, there is UART communication happening, and you have something known as the serial buffer register or the serial receive register in the Atmega controller that stores the 8 bits coming from the microcontroller, from another microcontroller through UART communication, and it has the actual characters. Okay, all the code for the video is in the description, so you can go on the drive link and download the code. In order to blink an LED, we'll achieve it through 3 steps. The first step being setting the DDR-B register bits for port B pin 5. The second is setting the pin 5 on port B to a high state, which is actually sending the high signal onto the port, and setting the pin 5 on port B to a low state. So starting with the first step is basically setting B pin 5 of the DDR-B register to 1, a binary 1. So if we look at line 7 of the code, that sets the port B pin 5 as an output. On the RHS, the equation is basically 1 left shifted DDB5. DDB5 represents basically the 5th position of the DDR-B register. So if you look at the output of 1 left shifted DDB5, it will be binary 1 on the 5th position with rest of them zeros. We can directly put that value inside DDR-B, but in some cases, when you add this, all of the other values will change. So if you wanted to use multiple ports as an output, you won't be able to do that. So to achieve that, we need to run an OR operation on the DDR-B port. So that is basically the pipe and equals to sign. That means DDR-B equals to DDR-B OR operation 1 left shifted DDB5. So we've got the answer of the 1 left shifted DDB5. We now do the OR with the DDR-B. So the final output of DDR-B will be binary 1 on the 5th position with zeros on the rest. So basically we've told the microcontroller as to keeping port B pin 5 or pin 13, physical pin 13 as an output. Coming to the next step is setting the port B pin 5 pin to a high state. That is basically the same we did for DDR-B. Just instead of addressing the DDR-B register, we'll address the port B register and we'll 1 left shift with port B5. Basically, it's telling the port B5 register to keep the pin 5 of the port B to a high state. The third step, which is lowering the pin, is basically we'll use the AND binary operation and the complement operation. So we'll perform the same 1 left shifted of port B5, but we'll complement it. So now it will add a 0 on the 5th position, and all of the remaining bits will be set to 1, and we basically AND an operation. We'll basically use the AND operation now. So we'll get the pin 5 of the port D to low state, and we'll not change anything else in this process. That's it for today's video. We'll keep on adding other videos like these, and we'll keep on adding new series and new electronics videos. So please stay tuned for the next videos, and please do like, share and subscribe the video.